My name is Fred Kim. I'm an engineer consultant at HBM Prancia, and one of my roles, and my primary role maybe, is to help promote VibeSys, nCode VibeSys. And today we're going to talk about modal analysis in nCode VibeSys, which is a brand new option that appeared in version 12.1 that was issued a couple of weeks ago, so very recently. So first, allow me just to show you this slide, just one slide about the product range we have in Prancia, and specifically the nCode product range. So on the top left, we've got Design Life. Design Life is it enables you to do fatigue calculation from finite element result files. So in finite element, you calculate stress typically, and in Design Life, you have those stress values to vary. And you end up with contour plots of life, fatigue life, whether it's random, shaker tests, things like that. So we can simulate what's going on either on a shaker or a test rig or in service. Glyphworks is a signal processing tool with specific capabilities for durability applications. So accelerated testing, for instance, to reduce the test duration at ISO damage and things like that, customer correlation in terms of severity, damage, etc. So it's a general purpose signal processing tool with loads of capabilities for fatigue and durability. Then we've got automation, and automation is good when you've got tons of signals, tons of tests, and you just want to organize all this and have dashboards to tell you, well, to retrieve easily data, share data with colleagues, and secure data. So it's basically a database on the top of which sits Glyphworks. It's an engineering database. And last but not least, we've got VibeSys, which is a fairly new product, and it's similar to Glyphworks, but instead of focusing on durability, this one, VibeSys, focuses on acoustics and vibration from an experimental viewpoint. So the input signals are acoustic signals or vibration signals typically, and we do quite a few analysis. So today we'll concentrate on VibeSys and more specifically on structural dynamics. So the content, the features of VibeSys are listed here. The main ones, like we've got capabilities for rotating machinery analysis. So that's when you want to troubleshoot what's going on an engine, a gearbox. So you're measuring some signals and you do some analysis to figure out what the orders are, if some noise is due to a specific shaft that's maybe not balanced, things like that. We've got another set of tools for human perceptions to acoustics and vibration. So that means for acoustics, we've got all the weighting functions to mimic the human ear, and therefore we derive some metrics and able to tell you how the sound is perceived. And similarly with the human body, like whole body vibration, hand-arm vibration. So the usual metrics that the ISO standard require you to calculate are calculated in here. And then we've got the structural dynamics. So we're going to concentrate on structural dynamics, and basically it's all around frequency response functions. So basically you've got a system, a structure, a machine that's vibrating, and you want to characterize its dynamic properties. We also have a vibration manager that contains a lot of spectrum coming from various standards, MIL standard 810, DOE 160, etc. So you can pick spectra from there and compare them with the measured spectra. So the benefits of VibeSys is really to do with the process-oriented look and feel, like you're building a process like a Lego game. You're just linking those icons that we call glyphs to build a process. Then you drop data in there, and it produces all the plots, displays, tables, everything you need. So It can be saved and reused and shared with other individuals throughout the company. So it's a very corporate tool, and it's got no limit in terms of the volume of data, channel numbers, and it has got a lot of functions, right? If you consider especially that it can be extended with Python scripting, MATLAB scripting as well. So it's quite a powerful tool. But let's concentrate on structural dynamics. So in VibeSys, I'll show you in a minute. I'll do a live demo, but basically you'll see that there is an area where you'll find a lot of tools for structural dynamics type analysis, and this includes an icon, a glyph that does frequency response function analysis with H1, H2 estimators for the gain. It also gives you the phase, coherence, and autotone cross spectra. Similarly, we've got the autocross correlation function between input and output. We can do waterfalls of FRFs, and that's quite useful when you want to check for linearities. So like if during time you increase the excitation on your shaker, for instance, if everything's linear, the response should increase proportionally. Therefore, the FRF, the gain of the FRF, for instance, should remain pretty much the same through time. So that's an interesting tool we can easily use in VibeSys. And then we can do some custom filters. So you give the signal a gain and a phase spectrum, and it'll filter the signal according to these filter characteristics. It can do convolution, which is quite similar, but in the time domain. It's got Hilbert transform capabilities. And once you've got the various plots, you can put cursors, whether vertical or horizontal cursors. And the nice thing about cursors, one of the nice things is they were used to calculate the damping ratio at various resonance peaks. But now I'll show you that we've got a tool for doing that does that for you. So structural dynamics, like the idea here, we've got a structure like this plate here, and we want to characterize its dynamics. So we excite this structure. It could be a hammer impact, or a sine sweep on a shaker, or a random profile used on a shaker. In this example, it's a random PSD that's used to excite our structure. And in various places, you typically position sensors. So in this case, we've got here an accelerometer, we've got here a strain rosette, here a strain gauge, and on the shaker table itself, we've got this control accelerometer that captures the excitation signal. So here, for instance, we've got the strain response at a specific location, and the idea is, let's see whether some frequencies are magnified. In other words, if this plate has natural frequencies within the excitation range, and at what frequencies do we have a resonance, and what are the characteristics of this resonance. So in order to do so, we compute the FRF, and here we represent the gain of the FRF, right? And so we see here we've got two modes. That's just an example. I made it up for the needs of this presentation. We've got two modes here at roughly 20 hertz and 200 hertz, so that those are frequencies which would magnify the response at this very place here by a gain of that much, right? So in terms of, we're coming from the durability and fatigue world, and we realize that if you excite a structure at one of its modal frequency, at one, it enters into resonance, and the excitation level gets multiplied, if you like, by this gain factor. So you can guess the stress will be much higher, and therefore the fatigue damage will be higher and the fatigue life shorter. So it's quite important to, even for structural engineers, to get to know whether there are natural frequencies within the frequency band of excitation. And here in the middle, you see it goes down to almost zero. That's an anti-resonance. That means this very point here sees no a displacement or strain or acceleration at this frequency, so that it means it doesn't move, right? At this frequency, this point stands still, it doesn't move at all, so it's in a node of a vibration. So in order to produce such plot, we've got this glyph, frequency response analysis glyph, and this one's producing the gain of the FRF between excitation in red and response in blue, the phase. So you see typical behaviors of the phase once we hit a resonance. The phase loses 180 degrees typically. It's also sometimes useful to look at the coherence, which is an indicator of how much the response is due to the excitation, right? Or linearity between response and excitation, causality, etc. So it's got many views, and it's quite useful to have a look at it. So now we've discussed the frequency of a resonance, but as displayed before, you know, a resonance shows a peak, and this peak may have different gain factors, the Q here. So for very, very light damped systems, like, I don't know, bells or crystal glass, right? You end up with a very, very low damping, right? So you end up with a very high peak, you know, going as if it was going to infinity. So you've got an infinite magnification at the resonant frequency. On the opposite way around, if you have rubber or very damped system, your FRF will be very flat at the resonant frequency, and the worst case is that it goes to critical damping, so the response dies out without doing even a cycle. So basically, we've got this mean of calculating this metric, say the C, you know, the ratio, the damping ratio C, that's calculated as the rate between the damping coefficient and the critical damping. And so this one goes up to 1 when we hit the critical damping, and when we're very low damped, it goes down to 0. So that's typically between 0 and 1, so 0% and 100%. Typically, structures like metallic structure, we expect damping ratios between, I don't know, node 1, a very small value, to 5-6%, depending on the joints, what you know, the structure, etc. So we don't have a damping ratio for a particular material. We have a damping ratio for a particular assembly, right, a particular structure, and at a particular frequency. So note that the frequency, the natural frequency, reduces with increased damping. That's a nice phenomenon. Like you see the one has a maximum that's below the frequency corresponding to the maximum at low damping. And so some people use the C factor, some others use the dynamic amplification Q factor, but there's a linear relationship between the two factors. So modal analysis. Basically, what's modal analysis? It's a process of characterizing the dynamics of a structure in terms of its dynamic properties. So those properties include, as we saw, the modal frequency, so the various frequencies of the various peaks here, the modal damping, so we want this C factor or the Q factor. So far I'll only use the C factor, so the damping ratio, and I'll use it in percent, so in this case 1%, 1.5, 2.1. And also what's very interesting to look at is the mode shape. So we'll come back to mode shape, but basically each frequency, each resonance has its own mode shape. So once you've, so the objectives of modal analysis are to define those three parameters, right? So why should you do a modal analysis? Well, nowadays we use FEA a lot, finite element analysis. And as soon as you do a dynamic analysis, whether it's a harmonic analysis, you know, you excite your model of a range of frequencies with sine waves, unitary sine waves at the various frequencies, right? or you want to do a transient dynamic analysis, model superposition, transient analysis. Well, for those analyses, sooner or later you'll have to set the damping ratio. What's the damping ratio? And typically people leave it by default 5% or 2%, and they leave it constant throughout all the natural frequencies. So using experimental model analysis enables you to set up this parameter properly, right? Coming from some test can only be better than leaving the default values. And you know, we're currently writing a paper for SAE 2017 where we'll show how important it is to set this property properly. Just as we said, you know, if there's a high magnification factor, then the stress will be magnified, the stress response, and therefore the fatigue damage will be exponentially impacted, right? So it's very important. Once you've got your finite element analysis done, especially your finite element model analysis, you may want to validate. Because as you know, if you are a structural analysis and if you're using finite element, the modeling is quite complicated. You've got boundary conditions, both in terms of constraints and application of the forces. You know, all these are models. Then you've got the mass of the structure. You've got the stiffness of the structure to take into account properly, etc. So you may as well end up with with some results that are far away from reality, right? From what's going on in the physical world. So the idea here is to do a simple model test and validate that the FE result file shows the same model frequencies. And for those model frequencies, it should show similar mode shapes as well. So we want to compare those, you know, on one hand the FEA, on the other hand the model tests, to validate that the FE model is, you know, it's reliable. You can continue your analysis, go to fatigue or whatever analysis you want to perform, stress analysis safely. Then other applications of experimental model analysis. So we're no longer talking FEAs. Troubleshoot noise and vibration problems. You've got strange noise. You want to know whether it's coming from a resonance. So you put some accelerometers and you give the structure hammer impact, and you'll get the FRF, and then you'll see. So that's quite useful for troubleshooting vibrations and noise problems. You may want to perform some structural health monitoring as well, because we know that if a crack appears somewhere, it'll change the stiffness locally, right? Depending on the crack size, of course, etc. But once you figure out the relationship between the presence of a crack, the stiffness, and therefore the frequency of the modes, you can, by simply tracking the frequency of the modes, you can spot whether a crack is appearing or not. There are techniques like that based on modal analysis. And last but not least, a very simple application but very useful. You do some improvement to the design, so you're changing your structure, you stiffen it here and there, or you change its thickness or whatever, and you just want to have a quick check whether the problem you had is indeed solved. So modal analysis is very good for that. You observe whether the natural frequency is still there, or if it has indeed moved to another frequency. So these are the motivation, and we strongly believe that it's useful to perform experimental model analysis, especially if you are in the FE world, because again, an FE analysis will always give you an answer. Is this answer reliable? That's the main question, right? So the concept of modal analysis, so in the black line is an FRF. Basically what we want to do is curve fit this black line by breaking it down into principal or say single degree of freedom systems. And each single degree of freedom FRF, if you like, has its own frequency and damping coefficient, damping ratio in this case. So that's what's called curve fitting or model parameter estimation. And basically that's the first step to obtain, well, the frequency damping of each mode and eventually the mode shapes. So I mentioned mode shapes. Maybe some of you are not aware of what a mode shape is. When you excite a structure near its natural frequency, it vibrates, taking a very typical shape, typical to that very natural frequency, right? And so if you sweep to the next natural frequency, it's gonna vibrate, taking another shape. So each natural frequency leads to a different shape, and there are as many mode shapes as there are natural frequencies, and therefore as there are degrees of freedom. And for instance, we've got a cantilever beam here, and it's got a first bending mode at low frequency, a second order bending mode at a higher frequency, and here we see a cubic-like bending mode, third order at a higher frequency. Another example is a plate, and you can do that in your lab. I don't know, maybe some of you have seen that on YouTube. It's quite funny to look at. You put a plate on your shaker and salt. You put salt on the top of this black plate, and you sweep the various frequencies. You go from I don't know, 5 Hertz to 1 kilohertz or 2 kilohertz, and you will see that the salt positions itself, on the plate according to the mode shape. It goes to nodes of vibration, as you can guess. And so, by sweeping the frequencies and looking at the salt, you can guess the various modes and the various mode shapes the plate takes. So it's quite funny. You can look for it on YouTube. So in order to perform all this in VibeSys, so it's nice. Now we know what experimental modal analysis is. What is it for? We know about mode shapes. So how to do that in VibeSys? Well, in VibeSys we've got 2 new glyphs. The first one is the experimental modal analysis glyph. So the EMA glyph. So it expects a gain and a phase in terms of FRFs, right? A gain and phase. And it asks you what sort of frequency range are you interested in, and it wants the natural frequencies, and it'll try to fit the curve, but first it'll extract the damping ratios for each mode, right? And the results, the first result is probably this table showing here we've got 3 modes. We selected 3 modes. Here the frequencies are recalled and the damping ratio are given. So 5%, 3%, etc. And also it gives you the regenerated or reconstructed FRF, and that's simply to be overlaid with the original FRF, with the measured FRF, and that enables you to just have a quick idea of how good the damping ratio, how good the model fit was. So it gives you more confidence into the damping coefficients. The damping ratio is calculated. So it's quite useful to indeed overlay the regenerated FRF with the measured FRF. So I'll give you a demo of this glyph in a minute. The other glyph, second glyph we have in VibeSys is the operating deflection shape, ODS, and this one enables you to animate a structure. So it needs the structure, a model of the structure. So it can be all sorts of files. Rely a lot on the finite element file formats so far, and the most famous one probably for ODS is the UNV universal file. So we read it natively. Then we need some displacement to animate the model with. So either as time series or FRF spectra, or model table that's given from the experimental modal analysis glyph. So those are the model coefficients. But basically, once you have, for instance, time series, you need to associate the various time series to the various nodes that you've got in your geometry, right? And this is done via a mapping. So we've got a mapping editor here, where you say, well, channel 1 is the gain, channel 2 is the phase, and those 2 channels will be associated with this node number in this direction. So you can do that manually, interactively, right? Via a text file. Once it's done, you can save it and reuse it, or use a text file from scratch that you've created. Or some metadata, for those of you who are familiar with nCode tools. Metadata, can be calculated up front, and they would populate this table automatically. So these are keywords and each, and they are associated with a value that's been calculated up front. I'll show you an example of the use of metadata. Quite powerful. And so once you've done this, you can animate your structure. So here, for instance, we've got 3 modes in this FRF, and we'll see the 3 mode shapes. We'll be able to animate those 3 mode shapes. I'll show you. So it's time for a demo now. Let me switch to my VibeSys. So here we are. This is VibeSys. For those of you who are familiar with nCode tools, here we've got Glyph, Design Life. Below we've got automation. Here we've got VibeSys. So if you click on VibeSys, you'll see an interface very similar to the one of GlyphWorks or Design Life. Here on the left-hand side, I've got some files, whether they're measurement files or finite element UNV geometry type files. And on the right-hand side, I've got my palette containing all the glyphs. And in there, you can see structural dynamics and human perception, rotating machinery, etc., etc. So here we're going to use those glyphs, especially the frequency response function glyph and the experimental modal analysis glyph, and also the ODS display, operating deflection shape display. So I'm not gonna build it from scratch. What I'm doing now, I built it up front, and now I'm gonna open it up. So that's a flow file that I'm opening up, and the beauty of a flow file is that all the settings are already in place, and I could have saved even the input files in there, and I just need to run it, right? So let's start with this very first example. This flow file contains 4 different workspaces, some of them showing demoing EMA, some others ODS or mode shapes. Let me start with the experimental modal analysis. Right? So here, it's a random test that we did. So we've got, let me display this signal. We've got some excitation signal. That's a random excitation signal. Its PSD corresponds to a given PSD shape taken from a standard or obtained via accelerated testing or whatever. But that's been measured on the shaker. That's the excitation signal. And then we've got a strain gauge signal in micrometers per meters, and we've got an acceleration response signal as well in G. So here the idea is I'm dragging the excitation here, and both, I could have many other responses. I'm dragging them all in this glyph here. And let me press run. So here it's doing a frequency response analysis. So I can display here the gain and phase for the 1-2 pair of channels. So clearly we see 1, 2, 3 modes here with the phase that goes along. And if I move to the next pair of channels, this is the gain and phase for the accelerometer, right? This is this pair of channels. So it's quite noisy. The strain gauge was quite noisy. Whereas the accelerometer signal gave a much cleaner FRF in this case. But nonetheless, we used the experimental modal analysis glyph here on both pairs of FRFs, right? So here it requires that, let me double click on it to see the properties. Each glyph has a number of properties, right? So in this example here, I'm telling it to work between 40 hertz and 480 hertz, which is enough for capturing my 3 model frequencies. My FRF type will be an accelerance type FRF, so G over newtons typically, and here it requires the user to input some of the frequencies. So the way I did it is I put some cursors in here, right? When you select a plot, you can put some X cursors, and then the next button, if you click on it, it gives you the coordinates of the cursors, right? So what I did is I copied this one, or Control-C, and then I pasted it in here, right? You can paste it here. Then it asks you for a correction for the residuals, so those are the modes that are outside the frequency range of interest. They do contribute to what's going on within your window. So there are some, here we can apply a correction for these modes. So those are two coefficients that are, and they're used primarily for the display. They're used for the display of the regenerated FRF. They won't change the results. So that's pretty much it. So I run it already. So we've got some results here. We've got those three frequencies that I've selected, three modes, the associated frequencies, and here we've got the damping ratio in %. So, and if you want to make sure that those have been calculated properly, right, or that they make sense, say, so you may want to overlay the regenerated FRF using those values with the original FRF. So let me just press play. So I've got the original one in red here and the regenerated one in blue. So if I overlay them, I see that it's not bad at all, right? So I can trust those values. It's done quite a good job. Now let's have a look at the acceleration. It's quite good as well. So that's another thing we're learning here, is that, you know, no matter the sort of sensors you've used to collect the response, you know, whether it's an accelerometer or a strain gauge, you can still derive the damping ratio from it, right? It'll be the same. Normally, it's the same damping ratio. So that's an experimental modal analysis on random signals. Some of you may use hammers to excite the structure and may want to do a hammer test. It's simpler in some cases. It doesn't require an expensive shaker. So for instance, let's have a look at this pair of signals here. We've got the hammer excitation signal. So basically, it's an impulse here. We've given the structure an impulse, and then it decays quite rapidly. So you can tell it decays quite rapidly. And below you've got the response in terms of acceleration at a specific location, and it also decays. Oh, it takes its time to decay, right? So there must be a very, very low damping for apparently one mode, because it looks like a sine wave. So let's compute again the frequency response function using this excitation and this response. So let me press run. So here I've zoomed, you know, and I've got my frequency response function around the frequencies I'm interested in. So I see a very clear peak here, and another one here, and another one in the beginning, and this one here in the middle. So I've got 4 modes here. Now, I want to be somewhat more clever than before. So for those of you who know GlyphWorks, for instance, you know that we've got this trick, this metadata manipulation glyph. So let's see what it does. Here I've asked for the cursors to be outputs in this pipe. And using this glyph, I'm now merging the values of the cursors as metadata with the data, which is my FRF. So, so that the experimental modal analysis glyph now, if I double click on it, I no longer need to type manually or even copy and paste or whatever. I just right click here and pick metadata, and I've got the coordinates of my cursors in the metadata. So I can change that, press run again, and the results will change accordingly because I've changed the natural frequencies, right? So that's a way to make it more automatic, say. Apart from that, it hasn't changed much. I've chosen start and end frequencies, and that's it. So let's have a look at the results. So we've got 4 modes here, and the damping ratio, indeed, one of them, the second mode, has a very, very low damping ratio, less than 0.1%. And indeed, if I now overlay, as I did before, the FRS, the original one with the reconstructed one, here, the reconstructed here with this method we're using, it's trying to find an anti-resonance between each modes, which sometimes makes sense, sometimes doesn't. In this case, it doesn't. But we don't really care in this case, because what we're after is this. We want a good curve fit at the modes, and indeed, in this case, it's good. So this mode has been very well curve fitted, and so this one, even the first one, very good. This one in the middle that was captured, maybe not as good, but I think it's acceptable. Still, again, better than when you do an FEA analysis and lift the default value for damping coefficient. I'd rather use the one that it's calculating here. So anyways, we've got this result here, and we think by looking at this plot that they're fairly reliable. So that's quite good. So as a remark, I could have used exponential and force windows. As a matter of fact, let me show you. We've got those available here: exponential window and force window. These are typically applied on hammer signals like that, time constant, and but here it didn't really require it to be applied. So I kept it simple. So that's it for the demo regarding experimental modal analysis. Now what I'm about to show you is the operating deflection shapes. So now we're talking animation of a structure, right? So here I've got an example frame of a helicopter. So that's a UNV file that contains the node numbers and coordinates, and some links between those nodes, and that's a frame of a helicopter, for instance. And I've measured service data displacements in service at each of these nodes here. So I've got all those signals here, right? Many signals recorded during a test, in service, whatever. So time series, signals of displacement at various places and various directions. For instance, at point 208, I've measured the displacement along y-axis, z-axis, etc., etc. So let me press run. So that's the ODS display glyph. It requires the input geometry and this signal, right, in inputs. The thing is, now I need to associate those signals with the various nodes. So I've got a button here that's called ODS mapping, and if I click on it, it suggests me some mapping. So we've got, because the auto configure is checked. So we've got here the channel number 1, 2, 3 corresponding to those channel numbers here. Don't know if you see that, but channel 1, channel 2, channel 3, the channel title that comes along, and typically those columns here are blank, and we need to enter that this one will be associated with node 211 or whatever in that direction, plus X or what. The thing is, the list is quite long, so we could use a file. But I'm going to be clever here. I see that in the title of the channel, I've got it. I've got 209, that's the node, and I've got plus X, that's the direction. So that's why I used a metadata calculator that did some string manipulations. It extracted 209 and plus X, those two strings from all the channel titles, and it created two metadata, the node and direction metadata. So in the ODS display and the properties, I'm just asking the mapping type to be not user, not file, but metadata. And it does it automatically for you, right? So you don't need to worry about the ODS mapping. Also in the UNV file, I should have done this, actually, thinking about it. We've got this information in the UNV file itself. And we read this as metadata. So with UNV files, you don't even need to use this calculator here. for other file formats. You may, you know, for geometries in other file formats, you may want to use this. So, anyways, what I'm going to do now is I'm going to animate it. So let's grab just a small section so that it's immediate, right? So I've run it, and I'm now clicking on this animation button. Let me put some scale factor so we see something, and let me press play. So it's building the animation. So it's building 600 frames, and then we can animate it as fast as we wish. And I'll show you with cursors we can play. And so let me go faster. Oh, that's too fast maybe. So we see now our structure moving. You know, as you can see, it's quite complex deflections. And here you see the cursor that goes on the signal, so such that I can pose it and go backwards a little bit and forward and blah blah blah. You see, but actually, looking at this displacements, I can't see any mode shape, or it's quite complex to extract anything useful from that. So one idea is maybe to focus on one particular frequency. So what I suggest is let's have a look at the frequency content of those signals. Let me just grab, and you'll see, so the basic DSP contains all sorts of interesting tools. One of them is the frequency spectrum glyph. So let's ask it to compute a spectrum to see the frequency content. And look at this. There is one frequency that clearly is much higher than the rest, and that's around 17.5, 18. So let's do that. Let's filter the signal around between, say, 17 and 19. So again, under basic DSP, I've got here a filter. So I'm going to remove that to keep it nice and clear. And I'm going to insert that in here. And I'm going to say, do a band pass filter between 17 and 19 hertz. And I'm going to select again a short time frame here. And I'm going to replay that, rerun that. And now I want to see it moving at this very specific frequency. Yeah, it's almost a pure tone, right? So I want to see this very natural frequency animated, but I want to see it also with the static shape in the background. So let me just do that by selecting the elements here. Now it's going to move with this bold wireframe structure as static. So let's go back into the animation and let's press play again. I might stop it and give it a higher scale factor so that we see something. So here it's building the animation again, and we'll see, we can already see it. I don't know how it goes with the WebEx, but you should be able to see this bending mode here, right? So at 17 hertz from in-service signals, you know, I can filter and display a mode shape, or I can do operating deflection shapes. So take the signal as it is and just display it. And I'm looking at my watch. It's almost 5, so I'm rushing to the last example. That's now I called it ODS, but I should have called it rather mode shapes. Now we're really focusing on mode shapes as opposed to operating or in-service deflection shapes. So let me drag in there a bracket or whatever. It's a simple model of a bracket in this very case. And I've got so I did some model tests, and I gathered some FRFs, gain and phase at the various nodes of this model, right? And here what happens is I want to animate this bracket, but no longer using a time series of displacements, but this time I want to use my FRFs, and I want to point to some frequencies corresponding, of course, to modal, to resonances, right, to animate the structure. So what did I do? I've got my FRFs in here. I'm here displaying just the gain FRFs, and I positioned 1, 2, 3 cursors in here. Again, I used the old trick of exporting the cursors in a pipe and the good old metadata manipulation glyph, such that this pipe here contains both the FRFs and the frequencies at which I want to animate this model. Now, what's left to do is again the mapping between the measurements and the nodes. So this time, what I did is I created a text file, a very simple text file. Or I did it once for good and saved it, right? So, so you end up having this text file that you can use and reuse. So I've got channel 1 and 2 corresponding to gain and phase that I'm going to associate to node this with this number in this direction. And now, you know, it knows that there are 3 mode shapes because of this pipe, and it knows its frequency. So using the blue arrows here, you can move. Don't know if that's obvious to you, but you can move from one mode shape to another, and of course animate them. So let's animate mode shape 1. Oh, forgot to run it. Sorry. Let's animate mode shape 1. So that's mode shape 1, right? It's actually fixed here, and the mode shape 1 is clearly a bending mode that we have here. And if I move to mode shape 2, that's my mode shape 2. And that's very good because, you know, if you've got the same structure that's modeled in finite elements, right? Let me show you this. This is an OP2 file coming from Nastran. So that's the same structure, but this time it's meshed, you know, with a high mesh density. We're trying to find out local stresses in various elements. So we've modeled that with a refined mesh, and what we did is first a modal analysis. Before doing any dynamic analysis, you have to do a modal analysis first. Well, it's preferable, right? So I can display the mode shapes. So here I've got the various modes that have been calculated, and I can animate. So that's still VibeSys, you know. Within VibeSys, you can animate the various mode shapes. So here I've got again my my bending mode. So and ideally, this mode shape should be similar to the first mode shape we got from the experimental analysis, right? At the same frequency. If this is the case, then bingo, you can safely use your FE model and go with stress analysis. For instance, here for random fatigue analysis, you know, you need some stresses at various frequencies. And as you can guess, you know, once you look at the stress that's in this element, you guess it's strongly dependent on the mode shapes, you know, on the model behavior, right, on the dynamics of the structure. If the dynamics are wrong, well, the stresses here will be completely wrong as well. So in order to have a good confidence in your model, your results, and therefore your fatigue analysis and your design in general, I would strongly recommend comparing FEA with a simple model test. I think that's it. So again, sorry for the issues we had with the audio in the beginning, but I'm glad I'm still within time. So it's almost 5. So hopefully we get time for a few